can make star formation histories that create galaxy spectra such that there's no galaxy that ever looked like that. And similarly, there are stars being discovered all the time that for which no stellar library spectrum fits them well, right? So both things, it's both the case that the models do not cover the data and the models cover the data. And we have to be able to deal with that situation. So that will be true in the examples I show. Okay, good. So let's talk a little bit about what I mean by these things, then we'll come back to the demo and see if we do any better. Obviously, we're going to do better, otherwise we wouldn't be talking about it. Okay, so what's the likelihood? So the likelihood, say you have a galaxy size. So this data set is galaxy size, right? So you have a measured size, and let's call that DI. And I'm calling it D so that it's the data. So this is one galaxy, or one source, it could be a galaxy or star. It's source I, and it has a measured size DI. So then you can write down what is the probability that you got that DI, given that the object that you're looking at is a star. This would be the likelihood that the thing is a star. It's the probability of the data given the model. That's what we call the likelihood. Now, there are actually other things in here other than that it's a star. Because in order to ask whether these data can be produced by a star, you also have to know things like about your errors. Right? You have to know like about your point spread function. You have to know about your errors. There's a whole bunch of other things you need to know here, which I'll just call I, because I don't want to deal with them. But there's a bunch of things about your experiment. You have to have a noise model, and an optical model, and data analysis pipeline, and all sorts of things here to even ask this question. So, and by the way, I'm going to use the word model a lot. And when I say model, this is what I mean by model. Your star model is your expression for the probability of the measurement you got given the assumption it's a star. Okay? And this is just an angular measurement. And the star model is very simple. The star model in this case is stars have no size. They're delta functions. Okay, that's this example we're using on here. But then there's another likelihood we have for the galaxy, which is the probability that the data are produced by a galaxy. But now, in addition to this information here, the galaxy also has a radius. I have to give this galaxy a radius because there's big galaxies and there's small galaxies. And now, if I wanted to ask about the likelihood, if I wanted to compare the likelihood, one way I could decide whether this data object is created by a star or a galaxy is I can just say which is more likely, the star or the galaxy, which has a higher value for this function. And that brings a couple of problems, and you see the problem that I was mentioning earlier. This model is very qualitatively different from this model because this model has no free parameters. But this model has a free parameter. So I have to make a decision about what to do with that free parameter. Any suggestions? Marginalize is what Corin must say, and he's right, you must marginalize. But before you marginalize, the first thing you might do is...
I'm just going to say words that end in eyes.
One is optimize. You might optimize before you... So one thing you could do is you could just say, is the best fit galaxy better or worse than the best fit star? And that's not a bad suggestion. The only problem is there are galaxies with really small sizes, as we saw in my demo. They're really small sizes. So if you're just willing to let this R get small, you can make this likelihood ratio always 1, exactly 1. So this is the problem. This case is a really degenerate case. There are much easier cases, and we'll look at one later. We'll look at one, the next example will be a little easier. But in this case, you have to marginalize. What does marginalize mean? It means I need to get rid of this parameter in a way that is neutral about this parameter. This parameter is a nuisance parameter. All I want to know is the object a star or is it a galaxy? I don't care about the radius. I just want to know what it's a star because, of course, with Bev Lohman, what we're thinking about is measuring the halo stars in the outskirts of our galaxy, finding all that nice substructure, and galaxies are getting in our way. We don't care about the galaxies. We want to get rid of them. So we just want to marginalize out that we don't care about this parameter. So if you have a nuisance parameter like this, what you do, of course, is you integrate it out, but you're not allowed to do this integral. That seems like a nice integral to do. You're not allowed to do that integral because this integral has wrong dimensions. So you have to put in something here that looks like this. Leaving myself a little space there. You have to put in some probability distribution for the Ri, and this, of course, is the prior. Note, you cannot marginalize without a prior. You might think you're marginalizing without a prior by putting 1 in here, but then your integral is dimensionally incorrect. So you are definitely putting something in there if you ever do this integral. Okay, good. So there's a prior here. Now, once I do that integral, then I can reliably call this the probability of the data, given it's a galaxy. And of course, my other information I don't care about. Okay, good. And now I have two things that are on an equal footing, and now I can compare those two things. And I can make a decision. That would be the marginalized likelihood ratio. I have a marginalized likelihood for the galaxy. I have a marginalized likelihood for the star. This marginalized likelihood was very easy. I marginalized over no free parameters. And then I can say which is more probable. There's only one problem, which is ringing in everyone's ears, which is what to do about this thing. Okay? So let me go one step further in marginalization. What if I marginalize even further and marginalize over the star-galaxy choice? So I just asked, what is the probability, the overall probability of this data point, just given my background information? What's this? Well, this is going to be a sum over all the possible outcomes, all the possible things which are only star and galaxy by assumption. Of course, I should also put in quasar, free-floating planet, nebula, all sorts of other things. I didn't, so there's only two things. So this is just the sum for Q goes from star to galaxy, P, Q, times the probability of the data given Q and this other information. See, I now have to marginalize over this star-galaxy choice, and that requires yet another probability, because stars and galaxies come in different numbers. This is another prior probability. In fact, this is identical to this integral here, it's just the trivial sum. It's the sum version of this integral here. Okay, good. So now, if I look at this, if I look at this object, this is the probability of my data point. And now, once I have a probability of data point, I can write down the probability of my whole data set. Right? I have a whole bunch of these objects, so that I can think about the probability of my entire data set. And dropping the I for a second, I can think of that as just the product over all the data of the probability of all the individual data points. And this is the truly marginalized likelihood. Like, that's hella marginalized. Right? That's marginalizing over everything. Every possible assignment of star galaxy, every size, everything I can do. That's the probability of my data set. But notice that's a pretty nice object, because the better my model is, the higher this probability will become. Right? So if I have a good model, if my models for stars and galaxies are good, that probability will be higher. And if my models for stars and galaxies are bad, the probability will be lower. You see, this is like an overall assessment of the quality of my model. But notice I had this scary prior here. And notice this probability here depends on that prior, right? Because it comes into that integral. So if I want to optimize, if I want to have the best description of my data I can have, I want to optimize this prior so that my whole data set seems very likely. See that? Now I'm thinking of the prior not as something that I got before I started the show, but something that I'm going to get during the show. Because as I said at the beginning, the pan-stars data are the best data I have. So I shouldn't be constructing my prior before we start observing pan-stars. We should observe pan-stars, take all the data, and determine our priors from pan-stars. How do we determine our priors from pan-stars? We determine them by optimizing the overall likelihood of the pan-stars data. Shall we? So the problem with this, the reason this is called this reasoning is called hierarchical, because now I'm going to rewrite this prior as a probability for this unknown parameter itself has to be parameterized with a new set of parameters, and these are the parameters we're going to optimize. And there's two other parameters in the model, which is the probability of star and probability of galaxy. So I have parameters to parameterize this prior, and then I have these probability parameters. And I'm going to optimize them all, shall we?
Can I ask?
Yes, please do.
You still haven't fixed your dimension problem, right? You have your R still in there.
Ah, good. This marginalization procedure does fix the dimension problem in a funny way, which is that imagine the star model has no parameters, and imagine the galaxy model has huge numbers of parameters. All the shapelet, where the galaxy is in shapelet space and its star formation history and its redshift. So this thing has thousands of parameters, and this has no parameters. Okay, so now you might think, well, there's no way I can do this comparison. But when I do this integral, this probability has to integrate to 1. Right? So this has to integrate to 1. So if I just did this part of the integral, it'd have to integrate to 1. So if the space inside this integral is enormous, the value of this prior everywhere has to be very, very small. And that penalizes the fact that this has a big space and that has a small space. So there's a competition between freedom and predictive power. So the star model has no freedom, so it has amazing predictive power. It says it's going to be a goddamn point source. Whereas the galaxy model has tons of freedom, which means it has less predictive power. And that means this prior is like low, it's lower at any one point. So that penalizes the freedom. And in principle, because this is all derivable just from the axioms of measure theory, this is the only thing you can do to penalize the non-complex model. At least I don't know anything else you're allowed to do.
David, at a much simpler level, don't you solve your dimension problem by the fact that P of R has units of 1 over R so that it can integrate up to unity?
Yeah, that's another way to think about it. And if this had many dimensions, it would have dimensions of all those things multiplied together. Yeah, that's right. That's another way to think about it. I actually find the dimensional way of thinking very valuable in these probability problems. Okay, so what I'm going to do, so I told you that I'm not going to fit this with the correct model. I'm going to fit with an incorrect model. So my incorrect model is, I'm just going to cut this into 4 quartiles of magnitude. So those are 4 magnitude quartiles. And then in every magnitude quartile, I'm going to model the distribution as being a mixture, just like this mixture here, of some probability of being a star times this delta function, which the stars are, plus some probability of being a galaxy plus times a smooth distribution for the galaxies. Okay, so you ready? Here they are. There's 4 models. You probably can't see them. The top one you can see the easiest. You see the top one? There's a peak. There's a peak at the...
Don't you guess that?
Oh, that's a very smart idea. There's a peak here on the stars. What's that peak? That peak is the delta function convolved with the errors for this sample. I convolved with the model with the errors so you can see it. If I hadn't convolved it with the errors, this would have been an arrow that goes to infinity because it's a delta function. So I convolved with the errors here, and there's a very narrow peak, which is a delta function convolved with the errors here at the star location. And then there's this really broad distribution, which is the distribution of sizes for the galaxies. And then I gave this some parameters. I gave this distribution some parameters so it could fit the shape of this. So it's a parameterized probability distribution. And you can see that as you go down in magnitude, the relative height of the galaxies increases relative to the stars, and the distribution of galaxies gets more compact. And how did I optimize this model? I optimized the global likelihood of all the data, meaning I did this huge marginalization, and then I tuned my parameters to optimize the likelihood of the data set, the total likelihood of the data set. And that's hierarchical because I'm using the data set to set my priors. That's all the word hierarchical means in this context. Okay, so let's see how it performs. So now I can do my likelihood comparisons. So here's the likelihood comparison. So now what I've done is I've just created the marginalized likelihood that it's a galaxy, marginalized likelihood that it's a star, and ratioed those. So this is a likelihood ratio, star to galaxy. And as I move the likelihood ratio cut around, this is assuming I have to drill metal, so I'm going to move a cut until I'm happy to drill metal. Then you can see as I make that cut very hard, my completeness starts to go down. but my purity goes up. So just like in the old case,